Hello everyone, welcome to Chem76A. This week we will learn about alcohols and thiols. Alcohols are a class of organic compounds which contain hydroxyl functional group. This group is written as OH group, and thiols are those organic compounds which contain sulfhydryl functional group which is written as SH. Both alcohols and thiols are one of the most important organic compounds. Alcohols are found in alcoholic beverages and they also act as important organic solvents. Alcohols can also be used as a precursors to make other organic compounds such as alkenes and aldehydes and ketones. Not only alcohols can be converted into alkenes, carboxylic acids, and carbonyl containing compounds, but those compounds can also be reconverted back to alcohols. Therefore, alcohols play a central role in interconversion of organic functional groups. Thiols, on the other hand, are known for their pungent smell. Uh, most bad smelling compounds such as smells from skunks, rotten eggs, and sewage are caused by thiols or other sulfur containing compounds. So let's begin with the alcohols first, and later on in this chapter we will discuss about thiols. The general notation for alcohols is ROH, where R is an alkyl chain or may even be a cyclic ring, and OH is the functional group. The functional group of an alcohol is an OH group which is bonded to a sp3 hybridized carbon as shown in this structure. The bond angles around the oxygen atom of the alcohol is approximately 109 degrees. The oxygen atom in alcohol functional group is also sp3 hybridized, and we know the bond angles in sp3 hybridization is 109.5, but because in case of OH functional group there are two lone pairs which has greater repulsion, and therefore the bond angle shown here is slightly less than the normal 109.5 degrees. So as stated earlier, oxygen in alcohol functional group is also sp3 hybridized, and the two sp3 hybrid orbitals of oxygen atom forms a sigma bond with one with the hydrogen atom as shown here, and the other sigma bond is formed with the carbon atom. The remaining sp3 hybrid orbital around the oxygen atom hold unshared pair of electrons. So this would be the uh, electron geometry around the oxygen atom. The IUPAC nomenclature of alcohols is quite similar to the nomenclature of alkanes with a few modifications. In alcohol nomenclature, first we identify the longest parent chain. The only modification is that the parent chain must contain the hydroxyl group on it. Even if it's not the longest chain, then we select the one which is the longest along with the OH functional group. Then we number the parent chain from that side, which gives the hydroxyl functional group the lowest possible number. And the third modification is that we change the suffix E in alkane to OL to represent that it is an alcohol. For example, let's consider this alcohol. In this case, our longest chain is the horizontal chain, and this longest chain also include the hydroxyl functional group. Now in this case we number from the side, which gives the alcohol functional group the lowest possible number, so therefore we will number from the right hand side. So that would be 1, 2, 3, 4, 5, 6, and 7. And we do have one alkyl substituent at number 4 position, so this is ethyl group. So therefore the name for this alcohol will be 4-ethyl. In case of alkane, it would have been heptane. So, but because it's an alcohol, so heptane will become, we will remove the E at the end and we will add ol. So therefore the complete name will be 4-ethyl. And remember, it's now heptane. We're gonna remove the E and add ol, is heptanol. And now we also need to identify the location of the OH group. So OH group is located at number 3, so therefore we will put 3 in front of heptanol. So the complete name of this example is 4-ethyl 3-heptanol. For simple alcohols, common names are also used. In common names, the alkyl group bonded to oxygen is followed by the word alcohol. For example, the name of the simplest alcohol is methyl alcohol, because OH group is connected to methyl group, so this is known as methyl alcohol. And if the alkyl group is a ethyl group, then it would be called ethyl alcohol or butyl alcohol or propyl alcohol. So all these are common names of alcohols. Some of the examples of IUPAC as well as common names of few common alcohols are shown here. The names in parentheses are common names, whereas the names on top are IUPAC names. It should be noted that for alcohol with 1 or 2 carbons, the location for OH group is not given. For example, if we have alcohol with 2 carbon chain length, then there is no need to specify that it is 1-ethanol, because OH group will always be at number 1 position. So we call this simply ethanol. However, with alcohols with 3 or more carbons, the locator number for hydroxyl group is shown in the front. In case of cyclic alcohols, number 1 position is always given to the hydroxyl group. So therefore, this cyclic alcohol is named as cis-3-methyl cyclohexanol, and in this case there is no need to write the locator number for OH group. There is no need to write 3-methyl 1-cyclohexanol, because this 1 is redundant, as OH group in cyclic alcohols always get number 1 position. So there is no need to write 1. In IUPAC system, compounds containing 2 hydroxyl groups are known as diols, and if an alcohol contains 3 hydroxyl groups, then it's known as triol. Generally, if an alcohol contains more than 3, we call those alcohols polyols. For example, the alcohol shown here contains 2 hydroxyl group, and the carbon chain has 2 carbons, so therefore it is an example of an diol. In the nomenclature of diol, we do show the location of each of the hydroxyl group, and the final letter E of the parent alkane is retained, and the name is followed by the suffix diol in case of alcohols containing 2 hydroxyl groups. So therefore the name of this compound, because it contains a carbon chain with two carbons, is derived from, the name is derived from ethane. We do not remove the E as in case of simple alcohols. We keep the E and we write diol at the end, and in the beginning we do show the location of hydroxyl group. So therefore the name is 1,2-ethane diol. The structure of 1,2-propane diol is shown here, and in the third example we have an alcohol with three hydroxyl groups and the carbon chain length is 3 carbons. So therefore this alcohol is based on propane. We write the whole name propane and the name is followed by triol, because this alcohol contains three hydroxyl group, and the location of these three hydroxyl groups are 1, 2, and 3. So complete name of this triol is 1,2,3 propane triol. Common names of these uh, alcohols or diols and triols are also given. So first one is ethylene glycol, the second one is propylene glycol, and the third compound is glycerol. Both of these glycols are used in antifreeze solutions, and the glycerol is a common product of lipid hydrolysis in after metabolism of food. Compounds containing hydroxyl group and carbon-carbon double bond are known as unsaturated alcohol. An example of an unsaturated alcohol is shown here. While naming these alcohols in IUPAC system, the double bond is shown by changing the infix of an parent alkane from ane to ene. For example, in the alcohol shown here, it contains 6 carbon chain and the double bond is located at number 2 position, and a hydroxyl group is located at number 1 position. Because the chain length of carbon atoms is 6, so therefore the parent chain is hex. If the compound would have been it would have been an alkane, then the name would have been hexanol. But because there is a double bond, this ane or an changes to en. We also need to show the location of the hydroxyl group. So the name is written as hexene to represent that this alcohol contains 6 carbon chain with a double bond, and the position of alcohol is shown in the middle of ene and ol. So that would 1 ol. So hexene 1 ol means that this alcohol contains 6 carbon chain with a double bond and OH group is at number 1 carbon. The location of the double bond is shown in front of the name. So because the double bond was located at number 2 carbon, so the name is 2-hexene 1 ol. In case the alkene is optically active or geometrically active, then we do show notations such as E or trans in the front if applicable. The functional group of alcohol contains oxygen, which is the second most electronegative element, as well as a hydrogen atom, which is one of the weakest electronegative element. Because of such a large electronegativity difference between oxygen and hydrogen, oxygen gets a partial negative charge and hydrogen gets a partially positive charge. Due to this charge separation, a dipole is created in the alcohol functional group, and hence alcohols are capable of interacting with each other and other polar compounds by dipole-dipole interactions. In dipole-dipole interactions, the attraction between the positive end of one dipole and the negative end of another dipole keeps two different molecules together. As learned in previous slide, alcohols interact with each other and other polar molecules by dipole-dipole interactions. When the positive end of the dipole is a hydrogen atom and the negative end of dipole is either fluorine, oxygen, or nitrogen, then that dipole-dipole interaction is known as hydrogen bonding. Hydrogen bonding in principle is similar to dipole-dipole interaction, but it is the strongest dipole-dipole interaction. The strength of hydrogen bonding in water is approximately 21 kilojoules per mole. Although it's one of the strongest, or it is the strongest intermolecular force, but it is still pretty weak as compared to the actual covalent bonds. Nevertheless, hydrogen bonds have a significant effect on physical properties of alcohols. Hydrogen bonds in case of ethanol are shown here. In this picture, we can see three different ethanol molecules are interacting with each other with the help of hydrogen bonding. This hydrogen bond keep these molecules packed strongly together, so therefore separation of alcohol molecules from each other would require significantly higher amount of energy. The effect of hydrogen bonding can be seen when we compare the boiling point of ethanol and dimethyl ether. Both ethanol and dimethyl ether are constitutional isomers of each other. That means that they contain same number of carbons, hydrogens, and oxygen atom. So molecular formula of both ethanol as well as ether or dimethyl ether is exactly same. It is C2H6 and O1. In case of ethanol, as we saw in previous slide, molecules are associated with each other due to the presence of hydrogen bonding. No such hydrogen bonds exist in case of dimethyl ether. In fact, dimethyl ether does not possess any kind of dipole-dipole interaction. Molecules of dimethyl ether are only held together by London dispersion forces. Therefore, the boiling point of these two different kind of molecules are dramatically different. Because ethanol has hydrogen bonding, uh, which keeps all ethanol molecules together, we require or we will need high amount of energy to break apart those molecules. So the transition from liquid to gas state will take place at considerably higher temperature. So this temperature at which the liquid molecules turn into gas is known as boiling point. If a compound has hydrogen bonding holding the molecules together, so this transition will need large amount of energy in order to break these hydrogen bonding, and hence the boiling point will be large, which is the case in case of ethanol. However, in dimethyl ether, no such hydrogen bonds exist, so therefore the separation of dimethyl ether molecules is quite easy, and hence this dimethyl ether boils at relatively low temperature of negative 24 degrees Celsius. A comparison of boiling points of alcohols and similarly sized alkanes are given in this table. As we can see that in case of alcohols, the boiling points are much larger if we compare them to similarly sized alkanes. This is due to the presence of hydrogen bonding, which makes their boiling points much higher. The presence of a hydroxyl group, which is polar, makes alcohols much more soluble in polar solvents such as water. One thing should be noted that as the carbon chain length increases in alcohols, the solubility of alcohol in water decreases. For example, the first three alcohols, that is methanol, ethanol, and propanol, they are infinitely soluble in water, because in these three alcohols, the non-polar part, that is the carbon chain, is small, and uh, the, pol- uh, the polar part, that is the hydroxyl group, dictates the solubility of the overall molecule. However, as the chain length grows, uh, for example, in case of butanol, now the carbon chain is 4 carbon long. So this is considerably strong enough. So then the solubility starts decreasing. Alcohols with 6 or more carbons in their parent chain are insoluble in water. Similarly, if we have more than one hydroxyl group, the solubility of alcohols increases uh, quite a bit in polar solvents such as water. As you can see that one butanol is only partially soluble in water. Only 8 gram of one butanol will dissolve in 100 gram of water. But in case of 1,4-butanediol, which contains two hydroxyl group, the solubility is infinite. So solubility depends on two factors: number of hydroxyl groups and the length of a parent carbon chain. Previously in chapter number 4, we learned about Bronsted and Lowry definition of acids and bases. According to this definition, any substance which donates a proton behaves as an acid. In dilute aqueous solutions, alcohols donate a proton from the hydroxyl functional group to waters, and thus alcohols act as an acid. However, alcohols have very high pKa values, thus they are extremely weak acids. The conjugate base of alcohol after the donation of proton is the alkoxide ion. Because alcohols are weak acids, and we know that weak acids make strong conjugate base, therefore alkoxide ions are strong bases. The strength of acidic character of various simple alcohols are given in this table. As you can see that the strength of these simple alcohols is comparable to water acidic strength. The higher molecular weight and water-soluble alcohols are weaker acids than water. So therefore, we can say that alcohols, although they are acidic, but they are not strong enough to react with weak bases such as sodium bicarbonate or sodium carbonate. But in presence of strong bases, they will act as an acid. The acidity of alcohols primarily depend on the degree of solvation and stabilization of alkoxide ion by a water molecule. For example, for small alcohols such as methanol or ethanol, their conjugate base or the alkoxide ion is pretty small. So this small alkoxide ion can be easily solvated by water molecule, which forms a solvation sphere around it, and the positive ends of hydrogen atom in water due to dipole or hydrogen bonding uh, makes this alkoxide ion more stable. So this is known as the solvation of uh, any anion. On the other hand, in case of large and bulky alcohols such as tertiary butyl alcohol, after donating the proton, the alkoxide ion is tertiary butoxide. Due to the bulky size of this butoxide, water cannot approach it that easily. So therefore, the solvation is less effective around it. So because water cannot form a solvation sphere around it, hence the alkoxide ion does not get stabilized. Therefore, it is less likely to donate a proton, and hence butoxide or the tertiary butanol is a weaker acid as compared to methanol.